So thank you very much for being here, and thank also to INVALSI for organizing this workshop conference. So the time is very limited. We have only 4 hours in total for the entire training. So I will try to squeeze as much possible information as possible. Normally these trainings take 3-4 days, sometimes a week. But we have to do something given the time that we are provided. You can ask me questions at any time. I would ask you, when you ask a question, formulate it as short as possible, so that we don't spend much time on these things. So the purpose of this training is to provide a brief overview on TIMSS. This is the largest contemporary large-scale assessment in education that is competing with PISA. And also to present briefly the design, the operational and also statistical complexities that are relevant to the analysis of large-scale assessment data. Whatever you hear on this workshop is going to apply also to other studies, not only to TIMSS. And all of the large-scale assessment studies share a lot of things in common, but they also have a lot of specifics that are pertinent to each large-scale assessment. So I hope that you're going to develop understanding and appreciation of these operational complexities, statistical and psychometric complexities, and what is their implication for analysis. So the main takeout from the training is don't use plain statistical software like plain SPSS or plain R, plain Stata, or any other, but use software that actually can support for large scale, for the complex assessment and sampling design, because this is something very important for the inferences that you're going to make. I have the feeling that actually with or without the microphone, it's the same. So I can free my hand and just shout to you without apologizing. It's for your good, for your best interest. Okay, so my point is use software that is available for that. There's several software packages that you can use. I will come back to the later stage of the presentation, but RALSA is just one of them. There are others like R packages like Diffie Survey, Ed Survey, INSVI. There is also the IDB analyzer the IDB analyzer of IEA itself. Okay, so did you all download the folder that you needed to download? The zip folder from that was sent to you by the organizers? Yeah. Did you all install the software?
Yes.
Okay.
Yes.
Good. Good. So in the folder you will find the data, of course, that we're going to need for this training, but also some of the documentations that are important. And there are many other things that are available on the website of the studies themselves, and also from the IEA. The IEA data repository contains complete databases with all materials that you will need. So what is TIMSS? As I said, that's the largest comparative study in education, quantitative and large scale. How many people are familiar with TIMSS?
What do you mean by familiar?
Have you at least read the international report? Okay.
Not the latest.
Not the latest. Me neither. Okay. I'm joking, of course. What about the technical report, TIMSS? User guide? Okay. So that's the largest comparative study that started in 1995 with its first release cycle. And it tests students in grade 4 and grade 8. The first cycle was also in grade 12. And it's repeated in every 4 years. So it is a cross-sectional study where it always goes and tests students in these two populations, but not the same students every next time. So it's not a longitudinal study or repeated design. So it tests mathematics and science, and in 2019 there were 72 educational systems in total. 8 of them were benchmarking participants, like Canada, Ontario, for example, or United States, Minnesota, or Belgium, Flemish. So it's quite a big study. It's repeated in every 4 years, and it has several instruments. It has also, besides the achievement test itself, it has contextual questions and background questions for parents, students, teachers, and school principals. And one of its strengths, as many other IE studies, is that it's curriculum-based. So the curriculum is taken into account when the test itself is designed and composed. Okay, so there are several background files. The student background file is about attitudes towards the subject, student home situation, reading habits related with studying and mathematics, daily routines. They also include the test scores. It is also for teacher, that it also has the classroom practices, and also attitudes towards teaching, and many other background characteristics of the teachers, the school, the background of the school, and home. This is the home background that is different questions responded by the parents or the guardians of the child. And then we also have achievement files that there is a bit of misunderstanding how things are done in teams. The student file, background files, also contains the final background scores. And the achievement items, the files, the so-called achievement files, contain only the items, the actual items as the students responded on them. So these are very, yeah.
I cannot find these slides in the presentations folder. Is this correct, or did I?
It should be PDF files there.
In the folder presentations?
Yeah.
And which presentation is it?
The first one.
Introduction?
Yeah.
Okay, sorry.
And it's the 5th slide, sorry, 6 in a row, yeah. So, the other thing is, because TIMSS is now transitioning since the last cycle in 2019 to fully electronic assessment, there is also additional complication with the files. So there are main files, which are the paper TIMSS and e-TIMSS files. Because some countries had the test in paper, some also had them in electronic format. And there are also bridge files for the countries that took the electronic assessment. TIMSS also provided with smaller sample of students the paper instruments, so that they can link and estimate what is actually the effect of transitioning from paper to electronic items, because there is some mode effect. And there is also separate files called problem-solving items files that include items from both the regular e-TIMSS, but also the complex complex tasks that require several steps that students need to take to complete. So there's a lot of information. Only the technical report is over 1,200 pages. So that's quite a lot of information. So I'm going to try to squeeze in the next presentation the design of TIMSS and what are the implications for analysis. Normally this will take at least a day, but we don't have so much time. So it's going to be kind of a crash course. So one very useful document from the entire database is the user guide, which is very helpful because most of the technical questions that you're going to have there, from the file and item naming convention until the actual analysis, are going to be answered there. So use software appropriate for the design, like RALSA, although there are many others. And you can reach the IEA data from the data repository. Here's the link. The OECD is less well organized than the IEA data. So you need to go and search through the website by yourself for every single year of PISA or TALIS. So before we start with the design, it's very important points to remember is that these are surveys. They are large-scale surveys. We know what the students can do at the moment when the surveys were implemented, and everything that they can do or are able to do is depending on many things that happened in the past. So you have been on the previous presentation where was raised the question about, again, the question about the causality of the results, and have in mind that causal inference with these data is very hard, if possible at all. So these are independent measures all the time with the same population of students or populations of students, but not with the same students themselves. So there is no longitudinal effect or repeated measures effect here. So we can, and all of this has to be respected when you reach to the analysis stage. Do you have any questions so far before I move to the next presentation? No? Or you don't know what to ask? Okay, so as I said earlier, this is a very short introduction to the design and the statistical complexities related with the analysis of large-scale assessments data. So some of the challenges that we face with large-scale assessment is that the domains themselves are very broad. So TIMSS tests mathematics and science. Each one of them is a very broad domain, and we don't have the time to devote to analyze everything possible in these studies. So we need to still select items that are the most appropriate and with that we are sure that they validly and reliably measure the constant that we measure. So we need some kind of a sensible design to limit ourselves in time and effort. And then we need to somehow summarize all the performance of these items. The other complication is that we cannot test everyone on everything, so we are choosing samples both of students and also samples of items. And this brings some unreliability or error, noise, call it the way you want, into these estimates. So when we sample students, but we also sample items from the entire pool of all possible items, this always results in some uncertainty, some error in our estimation. And we always need to estimate it and take it into account when we interpret our estimates and make our conclusions, especially if we're testing for significance of the difference or significance of the results. So the standard errors have two components. We have Betty. Можеш ли да вземеш снимки?
Може.
Yeah, и да ми пратиш. Yeah, sorry about this. So we have two sources of error. One of them is sampling error because of sampling of students. But the other one we also have, the other component is the error due to the measurement itself. So sampling and measurement always related with some uncertainty, no matter how precise we think we are. So I will go first with the sampling component of the errors. It is impossible to test everyone, of course, and this is why we're using sampling. And we know sampling from everyday life. Every time you cook soup, you don't eat the entire soup to say if it's well cooked. You just take 1 or 2 spoons, you taste some of the vegetables, some of the broth, you taste some of the meat, so you say, okay, it's salted enough, it's boiled enough, I can eat it. But you don't eat the entire soup to do that. The other example is when you go to the doctor and the doctor takes a blood sample, he doesn't take all of your blood out because this is going to kill you. But it's also not necessary because the blood is very well mixed in our bodies, moving all the time. And it's the same with the student population, so any other populations that you want to study. They're well mixed, or relatively well mixed. Some part of the populations maybe are not. Could be some geographical distribution depending on different characteristics. And one very popular technique is the simple random sampling that is very widely used in social studies. However, for the nature of large-scale assessments, it is not practical. Because first, it is too expensive. So what we know from the basic sampling theory is that 400 or more elements from a population is enough to make valid and reliable estimates. But now imagine that in a country as big as Italy, how many people live in Italy? 60 million people. Okay, so, but you have probably around, let's say, 5 million students. I don't know how many. And in grade 8, they're probably, let's say, 3 million. I'm just making up the numbers, I don't know. So imagine that you go around and sample 400 students all over Italy, and then you go and test each one of them all over Italy. That's going to be too expensive, especially now with the prices of the gas. And it's not even practical because it's going to take you a very long time and effort to do that. It will not be possible also because you test just one student somewhere in some schools but not in others. And it's very difficult to link the students with their learning context in school. So that's why the large-scale assessments use two-stage sampling, although there are some variations depending on the country size. So in the first stage of sampling with probability proportional to the size of the school, we sample 150 schools. What is meant by size of the schools? That's the number of students in the target grades, grade 4 or grade 8. So the larger schools have higher chance to be sampled, the smaller schools have a smaller chance to be sampled. And then within the second stage, we sample intact classes. So you go into a sample schools and you say, I take the entire class there. Now, this is different from simple random sampling procedures because, and also in systematic random sampling, because in this case, you would have equal probability of selection. This is the assumption of simple random sampling itself, and also of systematic random sampling. So, in probability with proportion to the size of the schools, this is of the sampling units. This is different because it depends on the size of the school itself. So, why we do it this way is availability of information, because not in all countries you have a complete register of all students in all schools and then on all classes that is very up to date. It reduces costs dramatically and also reduces the time. And it also ensures the presentation or representation of the target population groups. So it allows you also to achieve very good levels of precision, and it provides redundancy in terms of testing students with similar characteristics. But also the main thing is that we can link the students that we test with the context of their education, teachers and schools. So this is one of the things. I mean, we know that things are not happening isolated only with the students, but there are also many factors that are school related that are important, and we're interested in these. Okay, so now clearly we don't have a simple random sampling, we have something much more complex, but this is also increasing the complexity, because now we have a clustering effect. So the clusters, the people that are within each cluster, this is a class, we sample an entire class. They share many things in common. So they go to the same school because they live in the same area. So they share many things that are available in the area that are resources, for example. Do they have a library there? Maybe. Also social services and so on and so on. So this matters when we compute sampling errors. All the students resemble somehow each other because of the common things that they have together. Now, one important thing is that we need to make inferences for the population. We want to make inferences about all grade 8ers, 8th graders in the country, or 4th graders in the country. And this is why we need to use sampling weights. Sampling weights is we attach a number to each student. How many students with the same probability of being selected, these students share the same things with other students in the country. Now, the important thing is to remember is that these weights, different than simple environment sampling weights, are not equal. So every students from each school receive different weights depending on how big the school is. This is also reflected into them. They are adjusted for non-response, and also the sampling weights must be used always to get the correct population estimates. Now, the problem is that, what I said already, now we have way too many complications compared to other sampling methods. We have clustering of the students, but we also have probability of selection that is not equal across all schools. So we need to accommodate for the uncertainty that stems with these two factors, and one of the ways to do that is to use replicate samples. So the very short, and I have a demonstration on a later slide here, is to take the sample of all schools and all students that are within these schools, remove part of them, then compute an estimate, store it somewhere, and then restore the original school, remove another school, then recompute once again. And then you repeat this all over and over again, number of times, to estimate what is the first, the effect of clustering, and then the other thing is also the unequal probability of selection. So, and then we compute the variance in these estimates. So it may sound very complicated at the beginning, but it's actually a very simple procedure. So the variation of the replicates relative to the full sample estimates, this is to the full weight for all students and all schools, provides the measure of the variance in the full sample estimate. So what are the advantages is that it's convenient to use and it's easy to use, no matter how strange it sounds at the beginning and confusing. And it is applicable to most of the statistics. There are different ways to do that. PISA uses balanced repeated replication, and they say that this is the superior thing. IEA uses jackknife repeated replication, and they also say that this is the superior thing. But if you try to compare these with the same data, the two different approaches, you will get very similar estimates. They will be comparable. Now, how does it work in practice? You see this well? So, now, what you see here is how it works. We have 10 schools, and these 10 schools are grouped in pairs. So, first and the second sample school, the third and the fourth sample school, the fifth and the sixth, and so on. And for simplicity, I'm just having 2 students per school. Otherwise, it won't fit the spreadsheet here. But so we have jackknife zone indicator, that is pair 1 gets jackknife zone indicator 1. Pair 2 takes 2, pair 3 takes 3, 4, 5, so on and so on and so on. And then within each zone, I have a jackknifing zone indicator. So now remember that I said that at every step we delete one school, and then in the next step we recover it, then we delete another. And we compute in every step over and over and over again the estimates. So we also have assigned score for every single student. And then we have different weights. Now remember that I said we have different weights, different size of the weights for every single school, sometimes for every single student, it can happen. And then we have the full weight. That's the total weight of every single student. And then what we do is we're going to construct replicates of this full weight, taking into account the jackknifing zone and jackknifing replication information. So, how it goes? We go to the first school, and then within the first school, we have the jackknifing zone, which is 1. So we're gonna work now with this school to delete part of the sample students within this pair of schools. So for the first school in this pair, the jackknifing zone, jackknifing replication says 1. So we're gonna keep it, but we're not only gonna keep it, we're gonna double the original weight for every student. And then for the other two, for the second school in this pair, we're gonna, because it says 0, we're gonna delete them. And then using this replicate weight, we're going to, compute the weights for everyone. For everyone else, it's the weights are remaining the same. And then we compute the weighted mean of our score. It's 453 score points. So what we're going to do next is go the other way around and then take out the students from the first school in the pair and then double the weights. 9 by 2 is 18, 2 by 2 is 4. Double the weights for the second school in the pair. Then we recompute and we see that it's changing to 475. That's our score with the second replicate weight. And then we're gonna go over and over and over again through every single jackknifing zone, repeating the same procedure, and so on. So TIMSS is using 150 replicate weights because we have 150 schools. When we pair them, we have 75 replication zones. Then by 2, because we repeat this procedure twice for every zone, is 150 replicates. So that's quite a lot of computations. So this is the formula of the sampling variance, which is repeating what I said in the previous slides. So we take for every single replicate estimate, we take the difference of this replicate with the full weight for all schools together. We square them, we sum them, we divide by 2 because we repeat twice this procedure. And then we take the square root, and then we have the sampling variance. So this is the sampling error, the error that results from the sampling. Then the other one is the measurement error, or also called imputation error. So we sample also some, not only students, but we also select some items to present to them. And this is resulting in some error. What if it's not the items that we selected, but it's a different set of items? Would it matter? Well, it will, of course. And this is also resulting in this kind of error from the item response theory and conditioning models for estimating the student ability. I will go very briefly. IRT itself is something that takes years to master, and it's a complex framework, but don't have no time for that. So, because I said that we are taking only set of items, still there are quite a lot of them. In TIMSS, we have over 200 items in mathematics and over 200 items in science. So that's already quite a lot of workload for the students. So we cannot test all the students on all the items that we have. So what TIMSS is doing, and this is the electronic component of TIMSS, the electronic version of the test, we have different combinations. There are 14 of them, different combinations of items. And every combination of items contains one intact block for mathematics and science in each of the two parts. So the instrument is divided into two. So we take one in mathematics. M here at the end stands for mathematics, S stands for science. And so we present these items to them. Unfortunately, I don't know, do you see the highlighted in gray? Yeah. So we have 14 blocks that we pair in certain combinations across 14 booklets. So one thing that you will notice is that M02, that's the mathematics blocks item, is appearing in the first combination of tasks, but also in the second one. And it is the same with science block 2 that appears in the first combination, but also in the second. So these two combination of tasks, let's call them booklets or testlets, they have items in common. So I just highlighted here for the first three booklets. But if you go through the entire table, you will see that every next booklet combination of tasks is linked with set of common items to the next one. So this is called matrix sampling, multiple matrix sampling. There are also other names for that, like incomplete linked test design. So, but this means also that no two students actually, the students don't take all the items, but also no item is taken by all students. So the percent correct that we know from the classical test theory will just not work for estimating the student ability. And this is where comes the item response theory, where the response to an item depends first on the difficulty of the item, but also on the ability of the student. And in classical test theory, we just don't have that. We know how difficult an item is, but when it comes to computing the score of every single student, we don't take it into account. We just know how difficult it is, but it doesn't have any impact. So, so this is how it is addressing the limitation of classical test theory, and also the metric is not reference to particular population or item selection, but in reference to the relationship with the individual and the task. So simply put, what it means is that with IRT, it doesn't matter which sample you're going to use. So every time you take a different sample of students, quality sample of course, you will have the same item parameters, because with IRT you can estimate what is the desired, what is the needed level of ability to answer a certain item with certain probability. Okay, so now it also helps with multiple sampling matrix designs, where no student takes all items and no items is taken by all students. You've probably heard this before as vertical scaling. It's used as a term to describe this situation. So this is very different from, again, from classical test theory, because consider these two cases. We have two students, and one of them is jumping 2 meters high, and then 205, but then it fails at 210. So the other one can jump 150 and 155, but fails 160. So in both cases, we have 66% correct, but it's on a test with a different difficulty. So this is, and this is exactly what the IRT is overcoming. So we have in Tim's scaling procedure for first estimate the parameters of the items. So 3 parameter models is for multiple choice items, and then we have for short open-ended items with 2 scoring categories, true, false, correct, incorrect, 2 parameter models, and then we have a partial credit model for the polytonously scored open-ended items, incorrect, partially correct, and correct. So now, the other thing is that the estimation procedures for the scores with IRT are using, let's say, there's several actually. Estimated a posteriori, weighted likelihood estimate, and so on and so on and so on. They are shortcoming when it comes to estimating population parameters, population estimates. Because this is what we want to do with large-scale assessment data, is that they're going to be biased. They're optimal for individual assessment, but not for group assessment. So this is why the IRT is using something called the plausible values methodology, where we estimate, they're taking the context information of all students, all schools, and all teachers. They pull them together, and they draw, using principal component analysis, the information from the context questionnaires. So that's an additional component to the IRT that is used together with the item parameters to form population, not to form population, to form distribution of different groups of students with similar characteristics. And this is something completely different from classical test theory, but also from the regular IRT estimation procedures that are used. And then, because we have an uncertainty that is related with that, they also use, in TIMSS, but also in other studies, 5 random draws within the distribution of every single student to the group where he or she belongs. So now we have an additional complication that because of the imputation procedure itself, we have not just one score variable, but we have 5. So the number of scores actually differs across the studies. All IA student assessments use 5 plausible values. PISA uses 10 since PISA 2015 because they say, well, we want to be more precise. And this is why we're going to use 10. And yes, they're very, very, very precise at the 6th decimal point, which actually doesn't really justify the effort and also the investment into doing that, but okay. Okay, so these are not for individual reporting, so we cannot make an estimate for every single student and say, oh, you know, he achieves at that point, so we're going to assign him a grade of this one. So the procedure is to compute the statistics with each plausible value, average the results, and then compute the variance that is related with this estimate. Yes?
Short question. I'm wondering what we often do with this international large-scale assessment is that we report back the school results. And in this slide here, you are comparing the individual reporting as population reporting, but how do you, what would then be your conclusion for the school-based reporting?
It's not a short question.
Okay, it's a short question.
No, it's a short question, but the answer is very long. To make the answer short, very short, no. No. No, now leaving the joke side, there is a lot of issues related to that. The large-scale assessments are just not designed to do that. It would be good. Even in the past, the IEA had a version of the IDB analyzer that was doing school-level estimation for reporting back to schools. At the end, they suspended it. I was actually part of this version when I was working at the IEA. But there are a lot of pitfalls of the entire approach of reporting back to schools. I know that they're very interested, so you have to give them something back. The long answer of all this, you can have a look at the publication that I made on this topic at the IAETS Research Institute. It's school-level reports. And there I just proved that it's not really things to do, unbiased, in an unbiased way, but also that to do it in an unbiased way, you will need to change the design of the study. So you're going to have to sample at minimum 7,500 and or more students to be able to do that. And you have to change the entire sampling procedure, but you also have to change also the entire estimation procedure. So that's going to be very expensive for a country to do that. And I'm not sure that IEA would really go into that way, or Boston College or any other study center. So it's a short question, but it's not a short answer. The short answer is no. Okay. So at the end, this is the formula for computing the imputation variance that stems from all this complex procedure of distributing the items and presenting them to the students and then do all the fancy statistics. What it says is you take the statistic of interest computed with each plausible value, then take the average statistics and subtract it from the first one, this from this. And then adjust for the number of plausible values in your model, p minus 1, and then also make the overall adjustment of number of plausible values. Take the square root and then you have the imputation variance. And this is very different from the classical test theory where you have the measurement variance taken just by taking the square root of the difference between one and the reliability of the estimate. That's a very different thing. And it is same for the sampling variance, where with simple random sampling what you're going to do is take the square root of the standard deviation divided by the number of elements. The previous formula that I showed. So this is a very different thing, and it's stemming both between because of these complications that we have of the complex sampling procedures for both items and students. So when we combine the two formulas for the sampling variance and for the imputation variance, then we have finally the final standard error, which means that using the weights, the replicate weights, and the 5 plausible values, just to compute the average score of all students in Italy, in TIMSS, we need to make close to 800 computations, which is a lot. So, the first thing that do's and don'ts, never treat them as individual scores. This is not the final exam from school, or maturity exam, or just a regular summative exam. These are not not designed to report an individual level. Never use the average of 5. People tend to take this shortcut, you know, take the average of the 5 plausible values and they say, well, I'm gonna work with that. Because what you're doing then is that you're collapsing the variance that needs to be in these plausible values, and then you're underestimating the entire measurement variance, and you reach a wrong conclusion. Always use all of them, not just one, and repeat it separately with each plausible value when selecting the variables, when selecting people. Report the average of the statistics computed with each plausible value. And when conducting significance testing, combine the measurement variance with the sampling variance. That's very important. And here is an example from TIMSS 99 in New Zealand. We have the overall score in New Zealand, 491 points. We have the score for girls and for boys. And we say, okay, we have 8 score points of difference. So is it significant? So if we assume the sampling and measurement error together, what we get is 8.3 points of, of standard error. So okay, it is even bigger than the estimate itself, the estimated difference. So no, there is no statistically significant difference. But then somebody takes it and calculates it with just plain SPSS without taking into account the sampling variance, without taking into account the imputation variance, taking only the first plausible values and say, oh, it's 2.9. You see, there is a difference, significant difference between boys and girls. What are the consequences? This is a very simple example. But you're doing, let's say, something related with teacher variables. And then you go and advise your policymakers and say, oh, with the teachers we have to do this and this and this and that. Taking the second approach, you're just going to be wrong and going to advise a wrong policy. So, and again, there's plenty of software, no need to take shortcuts. It is there. There are currently 5 different softwares that are up to date and maintained, and they are also very generic softwares that you can use to do that on top of that. So we have 7 software products. Why taking a shortcut? Okay, so now we're coming to RALSA itself, the R package that we're going to use in this workshop for training purposes. So, as we said, when analyzing large-scale assessment data, take account for the design, take into account the sampling uncertainty, use weights and weight replicates, take into account the measurement uncertainty, which means use all plausible values, and don't use plain SPSS, R, SAS procedures that are available there. So this has to be your morning mantra when you get up from the bed and go to analyze data. So the IDB analyzer that you know is recently also has an R option. It appeared at the end of last year. No, publicly it appeared actually this year in March. There's 3 R packages that you see on the screen, and there is also the RALSA package that we're going to use there. So it is different from the other R packages that are available there. First that you don't need to specify the design yourself by hand unless you really want to. It just handles it, recognizes the data automatically and applies the correct procedure for that data set. And by that data set I mean for this study, because the studies have differences in the way that they do things. But also in this data set, depending who is in the data set for the same study. Is it just the student or is the teacher, which matters in terms of weighting and estimation procedure, or it is school and so on. it can work with more studies compared to the other R packages. You can use it both ways. You can use the usual way. Is anyone that is using actually R? No. And the other way is using the graphical user interface, which is very helpful. Hmm? Sorry? A graphical user interface where you can use the mouse and just point and click to make the settings. Whichever way you use it, it's doing the same thing. It's just a matter of convenience. It also creates Microsoft Excel outputs that are organized in different sheets for the different estimates, and requires a minimal familiarity with R. So there are not many things that you need to do to start using RALSA. You will see in a moment. And it prevents from common mistakes. So if you try to use the RALSA and you try to specify something that you shouldn't specify, it will just tell you, no, I'm not going to let you do that. You will see in a moment. And it also has extensive documentation, examples that are available on the support site of the package. See the link there. As of now, it supports these 15 studies, well, I hope that they're gonna, the number is going to increase in future. So 15 studies plus their spin-offs. Well, probably one day is also going to be able to work with the INVALSI data if there is interest in of INVALSI using this tool and make it available for their data sets. So, as I said earlier, you can use the syntax, you just write the call to the function. One thing that you will see in this code snippet is that you don't need to specify the weight, because RALSA will, in the background, search for the most appropriate weight for the respondents that are merged in this data set. As I said earlier, if you have student, it will be one thing, but if you have student plus teacher, it's going to be a completely different thing. So you also need this. So this is the I want to compute the mathematics achievement, the average of mathematics achievement of the students. I'm not going to specify all 5 plausible values. I will just provide the beginning of the name, the root of the plausible values name, and it will take all 5 of them. So, which is equivalent to this thing here, is just expressed in the user interface. Okay, so you have the materials, very briefly what the folder contains, the folder structure. So you have the data for grade 4 from Italy, France, and Spain. You also have the documentation, the presentations in PDF format. You also have the converted data, a folder where to store the converted data. I will explain in a moment why we need to do that first. Then, where the merged data are going to be saved. And then, where we're going to save the Excel outputs from the analysis. So, the workshop is using Teams Grade 4. The analysis steps are the same for Teams Grade 8. Whichever study you will choose, the analysis steps will be the same. But in the background, RALSA will do different things depending on the actual study requirements. How many replicates, how many zones, how many plausible values, and so on, and so what formulas, and so on. So So there are different design variables, how they are implemented in different studies. And also, for example, the procedures for merging the data. So in Teams, you can merge data between students and teachers, or only students from different countries. But you cannot merge only the teachers on their own, because they are not the sample of teachers from the entire country, but they are only the teachers that teach the sample of students, so they are follow-up sample. They cannot stand as a sample on their own. In ICCS and ICRS is going to be a different thing, because there it is the other way around. For example, in ICCS we don't have civic education subject in most countries, but the civic education is scattered across, let's say, in some countries it's a separate, could be a separate subject. In other countries can be part of social sciences and humanities. In some countries could be, I don't know, organized somehow. I cannot really give an example. How is it in Germany?
It's disputed because we have several education systems, 16.
16 is not several, that's, yeah. And you have the
and in
general government educational
and in
system.
some federal states at grade 8, there is a separate subject, and in other federal states at grade 8, there's no separate subject.
Yeah, which means that actually you cannot really link the students to the teachers, because you don't know which teacher is actually teaching some of the civic and citizenship concepts to the students. So you actually have a separate independent samples of students and teachers in the country. And therefore you cannot merge them. So, so RALSA will also take into account this for every single study. Also applying the correct weights and estimation techniques, so basically everything that I said so far. And now is the time that we start with the guided examples. I don't want to switch back and forth between the presentation and the software itself. This is why I have printed myself just to follow easier. All you need to do is to follow me. So I'm going to show on screen and we're going to do the examples together. Okay?
And is it okay to open RStudio for this, or to we?
Yeah, RStudio. I will show now. Yeah.
Sorry.
You see? No, it's not a problem. Okay. To look smarter, I'm even going to put glasses. Do I look smart enough? Thank you. Okay. Now, okay. So let's go seriously, because we have not have a lot of time. You are going to close this one. Okay, so excuse me for a moment, because I think that my laptop is not charging. So I don't know if this is working or not. The other two outlets are simply not working. Okay, so to start RALSA, go to your start menu and then type RStudio to find it easier, and then click on it to start it. Okay. And then what you need to do is go to the console here then type in the console library, and in the brackets RALSA. Okay. Okay, then you type that, just hit enter on the keyboard. And then RALSA will ask you, do you want to start the graphical user interface? Yes or no? Now type 1 and then press enter. Yeah. I still see people that are typing furiously on the keyboard, so I'm not quite sure what is happening.
Error in library once. Could not find library. I'm actually wrong way to library. Because it's down.
Library here. Yeah, because you need to click here. No, press Control Enter. But you again are now library. No, you are library. You're missing R. You are in a script, so we need to press Control Enter to exit. Okay, now it's asking me here. You need to click here. No, you need to press one. That's all. Press one and now it's good. Okay. Did it start? You are having some problem here. Okay. You have what is your username on this computer? Is it? Oh, you're missing a library here. Okay. Okay, I guess that when you were installing RALSA, you didn't say, dependencies equal true. Can you maybe work together with them? Because it seems that there is something on the computer that is not properly set. And now it's working. Okay. Okay. So what you're gonna see when you start this and RALSA loads is the welcoming screen, and then it explains what is it, what is its current functionality, and you see the two sections here below: preparation, to prepare data, and then analyze the data. One of the big things that normally even experienced our users are struggling with is manipulating the data before the analysis. And So click on data preparation, and the first thing that we always need to do when we start with a new data set, when we download it from IA or OECD, is to convert it into native R data sets, so that R can easily work with it. So click on convert data. Is it big enough that you see what is happening on the screen, even at the back? Do you see well there at the back? Yeah, okay. So click on choose source folder. And then we need to choose where the SPSS files that are provided by the IEA are stored. So navigate to the RALSA workshop folder. And then within this folder, just expand with these triangles next to it. You will see another folder, data, and then Teams 2019, and then grade 4. So you should see this thing. Don't try to click on these files, these are just previews. You cannot select separate files. So you will choose the entire folder, whatever is inside, whatever files. RALSA will try to convert them to our data sets. So once you have selected this folder, click on select. And now I have selected only 3 countries there in this folder. And you will see that RALSA already recognizes what is in this folder. It knows that it has data files from TIMS, and it knows that these are from 2019. It already knows that. So you can, so here on the left in this panel, we have the list of available countries, and we also have on the right side, we have a panel of which countries to select. Currently we didn't select any countries to select their data. So we can click on an individual country name and select them individually, or you can, with these double arrow buttons, you can move all of them. And vice versa, if you decide that you don't need any, you can just select one and then click any of these buttons, the upper button, to move it back on the left, to deselect it. I will just leave them all in there. The more the merrier. Now, when you scroll down, you will see one button, choose destination folder, where we're gonna save the converted data sets. So choose, click on it, and then go again to the RALSA workshop folder, and then go to work subfolder, expand it, and then go and click on converted data. Now, in your case, the right panel should be blank, because you're doing it for the first time. I have done it before at home when I was trying everything. So I will just override them. Okay, click on select. And now you see next to the choose destination folder, you see the full path to the where the data, converted data is going to be stored. And you also see here the syntax that is going to be passed in the background to R to do all the heavy duty. Okay, are you all there? Yeah. Okay, now click on execute syntax, and you will see when you scroll down from time to time, it's a good thing to do. You will see actually it's showing you the progress, what is happening in the moment. So it's going to take some time. The good thing about it is that when you start working with data sets from specific study or cycle, you need to do this only once in the beginning. Convert them and then just use the data. Now, why this conversion is necessary? Well, R actually provides libraries that can import SPSS data and SAS data. And they're doing relatively well. But in some cases, they produce unpredicted results for some of the variables. Sometimes they cannot really decode the property of the variable, like is it a character variable or numeric, or it is a numeric variable but it still has assigned value labels like a categorical would be. And sometimes these libraries are getting confused and they don't know what to do, and they either crash or they do apply some crazy settings to these variables. Another thing is that different cycles, different databases from different cycles are exported using different versions of SPSS. And the libraries in R that do that may sometimes not be really familiar with these different versions. So they don't date back to version 10, for example, that was used in, no, it was 8, it was Civet 99. And the last thing is that there is quite a lot of mistakes that were done in the databases themselves by the IA when they were exported. So wrong encoding of the labels, of the variables themselves, different number of categories in one country, but in another the smaller number, and so on and so on and so on. So, which is normal. I mean, everyone makes mistakes. What RALSA does is actually converting these things, because it's easier to use for the user, instead of every time when you import the data from SPSS directly into R, to fight with such issues. And the other thing is that it shortens the time for you because of this. You don't need to think about it even. And it's easier for R itself to work with native data sets instead of importing them every time. So some of the things that RALSA will do during this conversion is also to attach some additional attributes to the data sets and to the variables. So you see here at the top that it recognizes that it's a Teams data. It's because RALSA attaches an attribute to the team, to the data saying that it's Teams. Also the cycle, but also it will, some of the things that it will also do is, for example, to assign user-defined missings. So in SPSS you have these things, and you have them in the large-scale assessment data. That you have the general, just the cell is blank, but you also have the user-defined missing where the cell is not blank, but it's a missing value that is defined. And by default, R actually has only one missing value, which is NA, which means just plain blank. But sometimes these user-defined missing values may be very useful for somebody.
And now we can see that your computer is faster than, for instance, mine, and your computer is even much more faster than this. Why? How? Is that the explanation for these differences?
Yeah.
Okay.
Different computers have different power. You know. So I'm very happy that my computer is more powerful than yours, but I'm not happy that your computer is more powerful than mine.
Yes.
Why is your computer more powerful than yours? Okay. I don't know. To be honest, I don't know. You're using what, Windows 11? Okay. I don't know. I don't know. It's happening now. It's only Italy. Okay, okay. You just in Italy. Okay, so the other thing that I need to mention is for people that are using PISA data. PISA data is taking a different approach. So here we have in TIMSS and other IA studies, we have the data sets for every single country and for every single respondent within the country in a different data set, which is very convenient to merge and use, and use individual data sets. Unfortunately, PISA is taking an approach that I really don't understand, to put all the countries that participate in one file per respondent, which makes them very, very big and very inconvenient to work. So, I don't know. I think that IE treats researchers better than OECD does. But it's possible also to work with PISA data even from the older cycles, dating back to 2000, when the data was even not in SPSS but only in text. RALSA can also convert this one into R and make it more convenient. So we need to wait for another 4 data sets to finish. But we're getting closer.
Just two questions.
Yeah.
On the email it said don't use RStudio Cloud. Does it not work if you're just executing the code?
It will work. The problem is that these dialogues that you see, selecting folders, selecting files, cannot look when it's installed on the cloud. They cannot look from the cloud to your local drive.
But if you upload the data to the cloud drive, you can then point it to the cloud?
Yeah, you can do that, but you need to get a permission from your system administrator where to put it exactly. And the other thing is that the cloud in RStudio can be scattered. I mean, the actual presence of R and the packages that are installed can be on that server, but a cloud is usually across multiple servers. So you're going to have a lot of lag between the machines to get between each other, to access the data, write it somewhere, pull it from somewhere. The cloud can be distributed across multiple computers actually, so that's not very convenient. But yes, we can do that.
And the code that is put here at the bottom, like if we're writing just command line R, that's the extent of the code, or is there other hidden code?
You mean this
the
one?
Syntax? Yeah, is that the extent of the
That's
syntax?
the full syntax that you need. That's a code.
So if you're just doing it straight in R without the interface, you can just type that?
Yeah, you can type that by hand. Yeah. Okay, so I have already converted the data for myself. I'm sorry that I have a slow computer. Did it already finish on your computer, so it's still struggling?
We are in the same country.
Oh, you had a problem with right, still, yeah. Where is the... Aha, it finished. Okay. You can come back to... it should be open already. The browser oh, you closed it. Okay, it was not necessary. You need to, because it's still actually working the server. And then you can do the same thing like RALSA. You have it already. Then you can, because it's the library is already loaded, you can type RALSA GUI. And then press enter, and then it will open.
Thank you.
Oh, still working on that. Okay, open good. Okay, it seems that we need to wait. I mean, different computers work with different speeds, so we need to wait a bit. Oh. Yeah. Yeah, I'm sorry. It's the internet. No, it's I also work at the Okay, it seems that we're gonna have to wait a bit. This is actually the most time-consuming step in using RALSA. Everything else works much faster than that. I think that for Italy, when you compute the average of boys and girls, at least on my computer, I don't know, maybe on the computer it's a little faster, but it takes a second and a half for Italy. But here, I don't know why. I mean, this is really something that I don't understand with the data conversion. Okay, just see what is on the screen. And replicate this. Your colleague actually is going to use only Italian data, so she didn't convert the rest. So she actually can skip the next step. So the next thing that is important in RALSA is merging files from different countries, but also from different respondents. So now go to choose source folder. Click on this button. And then navigate again to RALSA workshop, but then go to work where we store the converted data files. So you should see this on the screen, converted data. This is where we set them as in the previous step. Okay, now select this folder and you will see again the three countries, or how many you converted. Spain, France, Italy, and then you will see nothing else at the bottom, below these. So now, there is a list of available countries data that is on the left, and you need to move it on the right, so countries that we're going to select. I'm going to take all of them, clicking on double arrow button, instead of selecting individual countries. And then, when you do that, and you scroll down below these two panels, you will also see list of respondents that are available in this folder. So it reads which respondents' data, and also from which study. It shows here on the top again. So we're going to choose the student background, and when you choose that, you will see another two panels that are at the bottom. Okay. One thing, I don't want this one to be here, the left panel. I'll just collapse it, free some space. Now you're gonna see that this panel actually also has one more column at the end saying respondent. So it shows you that it is coming from student background, ASG. Okay. Now I'm going to take all the variables and select them to be merged from all the three countries. I'm going to scroll down, and now we're going to merge, define the merged file name. I'm going to go to the RALSA workshop folder, then work, then merge data, and here I'm just going to type student, okay? Now I see. So yeah, it shows in this folder. then save.
Yes.
Yeah, you can just press save. Okay. Yeah, only student. Merge data. Converted data. No.
Flash.
Choose source folder. Converted data. Then in the previous step you converted the data somewhere else. Converted data.
Files are good, but the software is sick.
This is Firefox. Okay. Okay, let's do this. Okay. For some reason, Chrome is sometimes. Okay. Yeah. Firefox, yeah. Sometimes Firefox is not seeing things. Okay. All variables. And then define. Just like student. Press save. Yeah. Okay. So press save. And then press on execute syntax. And you're going to see that actually it's very close, it's less than 2 seconds, at least on my computer. I don't know about Herman. That is, everything is completed. Okay. Did it work for all of you? Yeah? Okay. Now, the next thing, and this is most of what people and our users are struggling with is recording the data. So the next function we're going to use, and you're going to see that it's much easier than, did anyone try to do it in R before? It's a pain in the neck. Okay, so we're going to choose a data file. Sorry, my mistake. I forgot to show you something else. Now, go to the previous screen, merge data. All settings should be available there still. And then uncheck the student background data. Uncheck it, yeah. And you'll see that the panels below will just disappear because we haven't selected anything to be merged. Now, go and check the last checkbox, ATG, teacher background. Okay. Now, remember what I said, that the teacher data shouldn't be used on their own. Because they always have to be, in order to use it, they always have to be merged with the student data. This is how it is by design for teams. So now, if you go and also check the ASG, you will see all the variables appear below. And you see in the last column of the available variables panel, you will see ASG, 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 and then it shows you that also there is a teacher data. ATG stands for teacher. So now, again, select all the variables, click on the double arrow button. Okay, we're going to select all variables. And now we have to define a different file to merge the student and teacher data file. And call it, I will call it student underscore teacher. Okay. press save. And now you see that actually the syntax that is going to be executed here has changed, you know, to accommodate for all the changes. So ASG stands for student, ATG stands for teacher. Okay? And then execute syntax again, and it will refresh the output at the bottom. So it took 5 seconds to merge all data. And this is very different from the converting the data, which is taking much shorter. Even Herman's laptop is working with it. So, okay. Now, the other thing that people are struggling with is recording the data or any alterations in data in R. So the next one is a graphical user interface, part of the application that is used to do that. Now we're going to choose the student file, and we're going to work actually with the student file until the rest of the workshop. So go and, okay, shall we give you a minute to help us with this?
Yes.
Yeah, maybe, but the computer is very slow, so maybe you just go ahead and...
Okay, yeah, we're going to have to wait for too long. Sorry? Okay, so in the record variables tab, just click on choose data file and then navigate to RALSA workshop, work, merge data, and choose student, the one that we merged first. Student. Not student and teacher, but student, okay? Click on select. So you will see again which is the study, which is the cycle, but on top of that you're going to see who is inside, student background. If you have more respondents, let's say student and teacher, that will be the second file, it will also be listed here. So it will always tell you what you have inside, not to get confused. Okay? And now, what we're going to do is we're going to record one variable, collapsing categories and reordering categories at the same time. So this is going to be the variable how much students agree that they like being at school. So it has 4 categories: agree a lot, agree a little, disagree a little, and disagree a lot. So we're going to take this variable and record it into a different one, into a new variable, where we will have 2 categories. The first one will be disagree, and the second one will be agree. So you see here at the top that there are filter boxes. The first one, this one, is where you can search for variables and filter them by the name of the variable. This is the first column, or label. So whenever you start typing, it is going to start filtering. So like being. Just a moment. Okay, agreed being at school. Okay, let's just say being. So this is the variable. The full question is how much do you agree with the following statements? I like being at school. Okay? So we're gonna take this variable, we're gonna mark it, and then we're gonna move it to the list of selected variables that we want to recode. So the other thing that you will see that you actually have already in the user interface some instructions. These are helping aids that tell you what is expected that you do. So when you scroll down, and here you have more instructions, we're not going to go over it. Believe me, I know what I'm doing. I hope at least. So you see the old numerical values for this variable. 1, 2, 3, 4, 5. agree a lot, agree a little, disagree a little, disagree a lot, and the last one is omitted or invalid. So this is a user-defined missing value. So what we're going to do, because I said we want to do it disagree, both of the categories will disagree to go into one and be the first one. So agree a lot will become two because we want it to be a second category. Then we're gonna say that it is going to be agree. Okay? The same for agree a little. Now, notice the warnings that are on the top. When you have defined less things that you are expected to define, then it's going to tell you, in this case, you have defined more values than labels, because I have here 2, but here I have only 1. So it's going to tell me, be careful what you're doing, you know, not to make a mistake. So I'm going to put here also agree. And this is going to become my second category. The first category will be disagree. Okay? Okay? And now, what it's still... Yeah.
Why are you taking 1 and 2 and not 0 and 1? So I like to have 0 and 1 because then I have to put in the second percentage.
Yeah. So this is because in SPSS you can do that. And I believe also in SAS. But R always starts counting from 1. So when you have categorical variables in R they're called factors. A factor cannot start from 0. It always starts from 1. So that's the reason. Okay, so now I have just one warning that is telling me, look, if you don't define the last one, I'm going to set it to NA, which is the plain missing value in R. But because the last one is actually a missing value, user-defined missing value, I can just skip it and recode it to NA. Plain. And this is actually what I'm going to do. I'm just going to ignore it, and this will automatically record it in the missing value, system missing value. So if I decide to do, however, to still assign it as a user-defined missing value, then I need to provide here a label for it, so it knows which one is going to become a system missing value. Okay? And now I want to keep the source variable that I'm going to record as it is, and I'm going to define a new variable name for the, so I'm going to record the variable into a new variable. So I'm going to define it as A, S, B, G, 10, A, recoded. I'm just going to add rec at the end. And I also can define a variable name for it, and I'm gonna say that this is the recoded like being at school. So I just know that it's that it's a recorded with the same value label. Okay? Are you there, all of you? No, I still see people clicking it, that's why.
Just a quick clarification, this is just that one item within the school belonging scale, it's not the whole school belonging scale. This is a single item of the school belonging scale, not the entire scale, correct?
No, it's just a single, yeah, it's a single item from this entire scale. So while we're waiting for the rest of the people, if you have multiple items and this is often happening with teams and also other studies that are on the same stem, then you also have the same response categories. So you can recode multiple items at once. So let's say, but if these they have different response categories, then the application will stop, hide the elements that you continue from, to prevent you from the mistake of recoding different coding schemes for different variables in the same way. So they have to be uniform. So if I take, as he said, as I take from the 10A, 10B, 10B, 10C, 10D, I can recode them all at once. Okay? So now click on Define Recorded Output File Name, then go to RALSA Workshop, and then Work, Merge Data, and then you can directly click on Student. So it's going to override it, and the good thing is that actually it even warns you. You're gonna override the file. But I'm not worried about it because I defined the variable name as a different variable name, so I'm gonna still keep the original variable there. Okay, click on Overwrite, and now you see the entire syntax that is going to execute it in the background. So it tells you which are the old values, which are the new values, and it also tells you what are the value labels. Okay? Okay, now scroll down and then click on the button Execute Syntax, and when you scroll down, call these messages, you will see on the left side of this small table, I'm sorry that it, for some reason here it's not very well displayed, but you will see the old one, the old values, and you will see the new values. So when you do the math, and add together the numbers for these two categories, you should get this one. Sorry, the second one, 0.5. So when you recode data, I have checked them already, so I know that the frequencies should be as they should be. But when you recode data, it's always good to have a look on this table that is produced in the output, and make the checks. Did it went well? The other thing is that if you switch back to RStudio, here this table is going to be also in the output, so you can, and it's going to be arranged better than here. I don't know why, for some reason it's just not displaying it well, but you can check it here. So the old one, and then you check the new one. Just add and see whether they went as they should be. Okay. Did it work for everyone? Nobody complaining? Okay. We have 5 minutes to the coffee break, so what would be your preference? To stop here and continue after the coffee break? To continue after the coffee break, or start now and make one more example and then go to the coffee break? Okay, which one is it?
From my perspective, we could do another example.
Okay, one more example. Okay. Okay, one more example and then we go for coffee. Okay, now we're going to compute the average mathematics achievement for, yeah, I think that some people already in coffee. Okay. Okay, so we are going to, Becky, you have some question there? No, if you have questions, just ask. Becky, Herman is asking questions and you're gonna have. Okay, so a very basic example is gonna become a bit more complicated later. when we reach linear regression. But now we're gonna compute the mathematics achievement of female and male students in the countries that we have in the merged file. So now you can collapse the data preparation tab and then expand analysis types. And then you will see the analyses that are currently available in RALSA. They are going to increase in the future, but for now we are having these ones. So if you click on percentages and means, you will see our favorite choose data file button. So click on it, and then go to RALSA workshop, work, merge data, and then student. Okay, so it tells you again where you are, who you have in this file. It's student, it's teams, it's 2019. So now, following the same logic that we had from the previous things that we have worked with, we have available variables, and on the right we have a set of panels for different variables. Now, so we said we want to compute mathematics achievement by boys and girls. So you can click on the labels filter box and type sex. Okay. So now what you're gonna see is that TIMS, and also in Pearls it's also like that. You have two variables on student sex. So the first one, ASBG01, is the self-reported sex. How students, responded to the questionnaire. However, some students just skip this questionnaire. It's not on purpose, they just didn't want to answer, or they didn't, or it wasn't purpose, they didn't want to answer, or they just overlooked it and so on. So there are some missing values, and there's also sometimes students make mistake marking boy instead of girl, or the other way around. So the second variable is a different thing. This is not collected by the student. It is collected by the school, and it's reported back to the
student listing form.
Yeah, the student listing form is reported back to the team that is making the study in the country. So, and then it's reported to the IEA, and they incorporate it in the database. So here you cannot have, at least in theory, missing data, and you cannot have, at least in theory, mistakes. So this one is more accurate than the other one. So click on student sex. And then against each panel you have these arrows. So we're gonna move it as a split variable. ID country is already there, and you cannot move it away. So all the results are going to be computed by country for every single country separately. So we're gonna move this one, IT sex, as a second splitting variable. Okay, and now we have to identify the mathematics score, because this is what we said we're going to be using. So if you type PV in the labels filter box, you're going to see that it's going to filter only plausible values. Now, one thing that you will notice, remember that I said that in TIMS we have 5 plausible values for every single score. Here in the interface, it will show you for every single type of plausible values, whether it is mathematics, it is science, or any of the subscales of mathematics and science. It will show you just one variable. So that's for convenience, instead of selecting manually all 5 of them and so on. So this is the root name of the main name of the each set of 5 plausible values. But when the computations are done, it will take all the 5. So don't worry about this. And then we're gonna mark this one, and then move it as a plausible value here. Okay. And then scroll down. Did you do it already? Yeah.
I made a mistake and I tried to reverse it and put it into background continuous variables.
Yeah,
And then I just have to put it back. Then I have to mark it again.
Yeah, you have to mark it.
Sorry. That's how it
It's
is.
okay. Okay, so one thing that you're gonna see here is that it automatically selects the correct weight. If you would have the error file that is student and teacher, it will select the teacher weight automatically. Now, in Teams we have more than one student weight. So if I decide, I can change this weight to house weight. But it will give me the house weight is going to treat the entire population as being big as the sample, as the size of the sample. Don't ask me why, it is still available there. If somebody wants to make inferences on sample level and not on population level, on the student population in the country, he can use the sample one, the house weight. There is another one that is called Senate weight, which makes the entire population being as big as 500. This doesn't really have an application here because we're estimating on population level. But when, for example, the scaling is done, whether it is for background or for achievement items, they apply in each country the Senate weight so that the bigger countries like Germany, which is 82, 83 million people, doesn't overtake smaller populations in countries like Luxembourg or even Liechtenstein, which is just 40,000 people. So then Germany would have a bigger say than Luxembourg into the item parameters. So for this reason, the Boston College has also produced the Senate weight, yes. So if you decide to move this one away and forget to put another weight or recover this one, then it will tell you that no weight is selected. So I will apply anyway the default. This is to prevent you from errors. Okay, so I'm gonna bring back the total weight. What? No, I'm searching by name. Overall weight. Okay? Okay, now there are three options here. You know from basic statistics what is mean, what is median, what is mode, right? Okay, so I'm gonna leave it as mean. And what else I'm gonna do is I'm gonna check the box produce graphs. So it will add also graphics into the output file. And then at the end I'm gonna click on the file output file name, go again to RALSA workshop, work, outputs, and I'm gonna say average math by sex. I've been trying all the things, all the exercises that are here, so I already have it. Just type or name it in a way that you will recognize what is it for your convenience. It's not necessary that it's the same name. Okay, define the file name, click on save or overwrite, and then at the end, last thing to do is, you see the check box here, open the output when done. So when all the computations are done, it will automatically bring the file. Okay, so click on execute syntax. It will start, it will show you programs in the console, and you see it was even less than a second and a half for iterating. So once it is done, and it will open the output in Excel. So a few things to notice. Actually, it is the output is in separate sheets. So if let's go first to the first sheet, which are the main results. So you see that it gives you how many cases you have in the sample for boys and how many for girls. It will also tell you what are the population estimates in Italy, how many boys and girls you have in the entire population. It has decimal points, simply because it's an estimation, so it's not that part of some student is missing somewhere. But it's an estimation of, because remember, we still have some error associated, so it's not necessary that it will sum up to a whole number. And then what is the error of this estimate? So it's plus minus 7,143 girls above and below number of girls that we estimated. It's an error. Don't forget we have a sample. Then we have percentages of boys and girls, and we also have the standard error of these percentages. Then we have the average achievement of boys and girls. So you see that in Italy, boys achieve slightly, well, it's not like slightly, it is how much? It's 13 score points more than the girls. But it's not such a big difference, because the scale of the plausible values, the center point is 500 points and the standard deviation is 100. So this is less than, yeah, it's a bit more than 1/10 of, a bit less than 1/10 of the standard deviation. So it's not something. The standard deviation is 100 and we have 13 score points difference. You sound like
I'm
okay.
surprised with regard to Italy, and perhaps this is very, not quite a question, but in Italy you have approximately the same number of boys and girls in the estimated population. And in France and Spain, the difference is really impressive high, especially in Spain. These are almost 3 million. And is this, in Germany, one reason can be that the sample does not cover the special needs schools, and in special needs schools there are more boys than but therefore we have more girls than.
How do you know that? There are more boys with special needs in schools with special needs.
In Germany that's the case.
I didn't know that.
Yes. There's also an explanation for this, but that's not our issue here. And I'm wondering whether, nevertheless, this is quite a huge difference in Spain and in France. Could be also sex selecting abortion.
I won't go that far. I mean, normally it's also not only across people, but it's also across animals. On average, there are more females than males. And this is how it goes. They're just more female than male individuals, also in humans, but also in animals. And it's in pretty much every country. It's not only about students, it's in the entire population. Also in my home country, we have with 3% more females than males.
The more is astonishing that we have more males.
We're in Italy.
No, in France and in Spain.
I don't know. I really don't know. I cannot answer why.
It's not a question for the show. I'm sorry for this.
No, it's okay. No, look, the other thing is that, remember that I said that there is also, yeah, I don't know. I just don't know. Maybe some girls decided to submit a test. Okay, so now we have the average of the plausible values, and we also have the standard errors that is associated with these estimates. One thing that you will also see, does the total standard error that takes into account the sampling but also the imputation variance. The big fuzzy formula that I presented the last time. And then we also have the two components of the standard error. So we have the sampling variance and we also have the measurement variance. This is in case somebody needs it. So we have also the total variance across the plausible values in every group that is defined by the split variables, ID country, and also student sex. We have the standard error. We have also the sampling variance of the variance, or the sampling error of the variance, and also the measurement variance of the variance, the imputation error. We also have the standard error, standard deviation, the standard error of the standard deviation, and so on and so on and so on. And at the end, we have the percentage missing in the plausible values. Now, one thing that I need to say is in plausible values, we, at least in TIMSS and PEARLS, but also in our IE studies, we cannot have missing values. If we have missing values, plausible values, then it means that the student just didn't take the test. He was not there, so he's not part of the study at all, and he's moved out. Okay, the second sheet contains the graphical representation of the percentages of boys and girls. So you see them in France, in Italy, and you see them also in Spain. And what you also have here are confidence intervals about the averages, you know, plus minus 1.96 standard errors, pretty standard stuff. And you see that actually in France, males are achieving much higher than girls in Italy. Now that's a classical example of why, in general, confidence interval should be taken with caution. Now, tell me, is this difference statistically significant? This is very often why people are constructing confidence intervals to say if something is statistically different. And this is a typical example in textbooks saying, don't rely too much on them because you're getting into this case. So, is this difference statistically significant? I would say no. It's a borderline case, you know. So we're gonna test this a bit later to be more sure. And it's, yeah, okay, here we can say, but still. Okay, then you also have the analysis information. It tells you which data was used for every single country. It will tell you which weight, which cycle, TIMSS, and also it will tell you how many replicates we used in this. The last one is, as of now, uninformative. If you use it, write in your own code, you know, to call RALSA from the RStudio itself. He is also going to put the calling syntax from that you see here on the screen. For some reason, it is just looking in the wrong environment, and I don't know how to fix that. But if you use it in RStudio, write in your own code to call the function, then it's going to put it here as well. So that's very useful if you try to replicate later the same analysis. Okay, now let's go and have coffee, and then we come back.
4:30.
4:30.
Yeah.
Sharp. So what this means is we're gonna compute in every single country which score corresponds to certain point in the distribution of achievement. Okay? So go to the RALSA interface and then click on percentiles. Then we're going to choose the same student data file. Work, merge data, and then student. Okay? Select this one. And you're going to see somewhat similar interface as in the other analysis type that we just did, the percentages and means. So now we're gonna do it. We're not gonna do it. Okay, we're gonna do it by student sex again. So we're gonna choose the IT sex variable. We can just search for it. Okay, sex of students. Add it as a splitting variable. I'll scroll down. One thing that I forgot to say when I was talking about when I was presenting the percentages and means analysis, you have different panels for background continuous variables, and you also have a different one for plausible values. So these are two different types of data. So plausible values are 5 variables that are analyzed together. Background variables are single variables. These, for example, are the background scales, like student bullying scale, that is composed from many different items, taking together the information from many different items. So they can virtually take any kind of value. They're not categorical variables. So this is the difference between these two types of variables. So now we're gonna take this time the not the mathematics but the science achievement. So type PV in the label box, filter box, and you will see all the plausible value scores. So click on the second one, which is the first to fifth plausible values in science, and move them to plausible values on the right. Okay. Now leave the weight variable as it is, and now you see here there is a box that says first, 25th, 50th, 75th, 90th. So these are values that are default, and you can change them. So we're gonna do the 5th, the 50th, and the 95th. So we can just delete the rest of the values. So just split them by, leave them split by, with a space in between. So later, if you change your mind, you can always reset them to the defaults, clicking on this button. Now, click again on Produce Graphs. And then at the end, define output file name. Go to RALSA Workshop, Work, Outputs, and then name it as percentiles. Click on Save. And then at the end, you see the syntax that is going to be executed. Click on Execute Syntax. Okay? And very shortly it's going to rise and shine in front of you. So now you have the scores. Let's go column by column. Again, I have the males and females, how many cases in the sample, how many cases, students in the population of 4th graders. It corresponds to the standard errors of it, the percentages and the standard errors of male and female students. And then you have these columns here, percentiles, 5th percentile. So what is the score in Italy for boys and girls that corresponds to 25% of the distribution of scores? So you see that for girls it is 396, and for boys it is 402. You also have the standard error and its components, the sampling and the imputation, the measurement variance. Then you have the same for the 50th percentile. So this is the median, actually. The 50th percentile corresponds to the median. And you have also the standard error for it. You see that again for boys, 50th percentile of the scores is slightly higher than for girls, and then we go to the 95th and so on. Now, if you switch to the second sheet in the workbook, you will have again the percentages of boys and girls per country, because this is our second splitting variable. And then what you're gonna have in the second set of graphs, you're gonna have the percentiles graphically represented for boys and girls for every single percentile, 5th, 50th, and 95th. And you're also gonna have the confidence intervals for these. And you're gonna have also the legend and so on. You're gonna have also the analysis information, and that's pretty much by it. So we see that in Italy, on average, the 50 percentile of the student scores in science are higher than for girls. Okay, so you also see that the standard errors, the difference in the scores, small, but you see that actually the standard errors are big enough to reject the hypothesis that they are different. And when you look on the graphs, you will also see here that they just overlap. Okay, any questions?
Yes, one question. You are using here, or the program is using red and green. And there are some people who are red and green blind. Therefore, I'm wondering whether there's an option to tell the RALSA that in principle it should be not red and green, but let's say green and blue.
Okay, to be honest, I didn't think about it, but you're right actually. If somebody is colorblind, he won't be able to see, to distinguish these two colors. Yeah, you're right. Yeah, I didn't think about this, but I should probably change it. This is the, actually it's not a question only for me, it's also the question for the people that produce the ggplot package. Because it's set by default there, so it just picks from the palette that is implemented there. Yeah, I have to think about this, how to change them to something more friendly color scheme.
95% of people don't have a problem.
Yeah, but these 5% that have, they really won't be able to tell the difference. Yeah, I have to think about it, how to change it to something else. The other thing is that the more splitting variables you add, then the more splits you're gonna have. Then
Yes, but these are the two colors they pick first, and at least first they could pick the 10th color then is red when you start with green or so.
I know what you mean.
What happens if you change the default theme of R before you run RALSA? Would that do it?
I guess. I didn't try it, but I think it should. I mean, I'm now trying with more categories to see what's gonna be the difference with the previous one. Okay, now it's red, green, and blue. Yeah, I have to, but thank you for noticing this. It's a good point. Okay, let's go to another example. Do you have any other questions? Let's go to the other example. Now we're gonna compute benchmarks of mathematics scores. So now consider the previous analysis. We were trying to figure out which number of score points correspond to different points in the distribution. This one is the other way around. It tells you what percent of students can reach or surpass a certain number of score points. And let's load the file and make the settings, and then I will explain further about the benchmarks. So go again to RALSA workshop, work, merge data, student. Now, you have two options here that you can use. One of them is discrete, which computes the percentage of respondents in the population within the boundaries specified by the benchmark values. The other one is a bit different. So it always accumulates the percentage of previous the students that achieve at the lower points to the highest. It's like cumulative frequencies in SPSS. You can think about it this way. So let's leave it as discrete, because we want to know the percentage for every single, and it's just easier to work to answer this question. And then if you scroll down, and we're not gonna split by anything, but we're gonna take the mathematics plausible values, filter them. It is the first one. And we're gonna add them to plausible values. Okay? And if you scroll down, you will see the default benchmarks for TIMSS. Now, different studies have different benchmark levels. They're different in ICCS, they're different also in ICLS. And PISA is a very special case where they're not different only from all other studies, but they're different even across cycles. So in every single cycle they have their own set of values. So depending on the data that you're going to load into RALSA, it will automatically select the right the right benchmark levels for that study and also for that cycle. It's also the case with ICCS, where the first two cycles had one set of benchmark, but they added one more. Even this case is handled by RALSA. So the default ones will always be applied per study. And now, because we want only the 475 and 550, we can just delete the rest. Okay? And if we want to recover them, we can use reset. Okay? Click on produce graphs. And then define the output file name. Uh, 475 and 550, maybe I just zoom it a bit. You see it better now? Okay. Okay, define the output file name. RALSA workshop, work, outputs. Yeah, it's discrete. And name it as benchmarks or something that you prefer, and click on save. So this is how it should look. And then the last step, of course, is to press on the button execute syntax. Okay. And it will open the output in front of you. So you see the percentage of students in the sample and also in the population that reach 475, but are below 475. So we have in France 43% that are like that. In Italy, you have 27%, and 42%, 43% of students are achieving between 475 but less than 550. They even have labels. 550 is advanced. No, 550 is, I forgot. They have labels attached to each one of these benchmarks. And you see that 30%, a bit more than 30% in Italy achieving over 550, which is a quite good result, I would say. Now, when you go on graphs, you're gonna see, because we have now only percentages, you don't have any names. You're gonna see, you know, bar graphs with confidence intervals, you know, for the percentages. And you see that in Italy, most of the students actually are between 475 and 550. One more feature of this analysis type is that for discrete ones, for the discrete benchmarks, you can also compute the average of continuous background variable that is within each group that is defined by the benchmarks. So if you type here SCL, you will see background scales that are computed by Boston College and added. So they use IoT to compute continuous variables that incorporate the information from many other variables, from categorical variables. But then they produce a continuous variable with center point of 10 and standard deviation of 2. So we can compute for every single group of students that is defined by the benchmarks, you can compute also the average of such a variable. So let's say, because we're using the mathematics scale, so let's say students like learning mathematics, which is this one, ASVGSLM, and then add it as analysis background continuous variable. Okay? Now, one thing, if you forgot, because I'm not gonna change the output name. If you forgot to close the Excel output, close it now, because then it will be overwritten. If it's open, Windows will not allow to be overwritten. Okay? Now, again, delete here the other benchmarks and leave only 475 and 550. Okay. Scroll down and then execute syntax. It's going to take a bit longer time because now we have more computations to do, but it's still quite fast. I mean, it did it in 16 seconds. So now what you're going to see is the same output for the benchmarks, below 475, 75 to 550, and then you're also going to have the average of this variable student likes learning mathematics. So you see that actually in Italy, there is not much difference between the students that classify in the three groups, below 475, 75 to 550, and above 550. So there's small differences. So this doesn't really can tell us if this variable is the one that explains these differences between the groups. but it could be something else. You know, I'm not familiar with the Italian educational context, so I cannot tell what this would be. But you're the researchers, maybe you know better than I do, and can find such a variable in the database. Okay, the next one is cross tabulations. So now what we're gonna do is to compute a cross table, two-way cross table between two different variables. And we're also gonna produce graphs for it and test for the significance of the difference between these, significance of the relationship between these variables. So go to choose data file and choose again the students. Okay. Now scroll a bit down, and here you see two panels that are background row variable and background row, column variable. So we need to define which is going to be split by what. So it's going to be a cross table between these two. So now let's take student sex, the one that we already know. So sex, IT sex, and put it as a row variable. Okay, so this is going to be our horizontal split. And now go and identify like learning science. Okay, students like learning science. Yes, you're right. We're gonna choose only the index. Now, thank you for pointing that out, because I was going to make this mistake now. The Boston College, when they produce these variables, scales and indices, they use terminology that is confusing everyone else. So they call scales the continuous variables that they produced using IRT. But then from them, they splitted these continuous variables into categorical variables from 2, then from 2, and then from 2. Usually they have 3 categories. And then they call these indices. But from scaling methodology point of view, this distinction actually makes absolutely no sense, because scale and index is completely different thing in the psychometric theory. So I don't really understand why they chose these names and how they exactly distinguish between them, but okay. So we're choosing the index, the one that ends with IDX here. So it points us that actually it's a categorical variable. Okay, so I'm gonna add it as background column variable, so it's gonna be our vertical split. Okay, and then I will choose produce graphs. Then define the output file name, the usual path.
It's a little bit too fast now, because there are so many other options where we could fit. The
Yeah.
expected accounts, complete the row, percentages. Oh, that's interesting. Why aren't we interested also in the row percentages, column percentages?
Yeah, you can be, but then the more you click on these options, the more redundant is going to be the output, and you're gonna get lost. It's not that you shouldn't, of course. If you're interested in these things, go ahead and do it for a paper for publication. I don't do it, and they by default they unchecked, just because not everyone is interested in these. But you can always choose them. Now, for the simplicity of the training here and the presentation of how to use the software, I'm not gonna check them. If you want, go ahead and check them, but you're gonna have to wait longer time because you have more computations to do.
I just didn't want to see this out without having read them.
Ah, okay. Ordnung und Disziplin. Okay. Defines output file name, outputs, and then we're gonna say cross tabs. Okay? Something's happening outside. I don't know. Okay, now click on execute syntax. Okay. Spain is done. France is done. Somebody working something else. Okay. So now you have again number of cases for each category that is defined by the student sex, female, male. How much is the observed count and how much is the actual expected count. So you see that there are some differences. You see also the standard errors of the split by gender, learning science, how much students learning like learning science. So yeah, to come back to Herman's, you see also the totals. So to come back to Herman's, if you click all of these, you're gonna have very big table and very redundant table that is hard to read. If you really need it for the analysis that you're trying to do and for the point that you're trying to make, go ahead and choose it. But then have in mind that you're gonna have to spend a lot of much more time. The other thing that you have here in the next sheet is testing for significance. So you have chi-square, the degrees of freedom of chi-square, and the p-values. Now, you have this twice for every country. Now have in mind that what it's doing is doing it, look at the second column. It says first and second order RALSA chi-square. So these are adjustments that are done by two statisticians, and they work together quite a long time on these two to come up with. Why these adjustments are needed when it comes to chi-square is that when we have a clustered data, we have the problem of bias when estimating chi-square in such cases in cross-tabulations and for categorical variables. So this is actually discovered in the mid-1970s, I think. And these two came with adjustment of these statistics, for cluster design. These are not the only ones, but there is one, there are many others. I think that there are 5 or 6 other adjustments for the same problem of clustering when you test for a relationship between two variables with chi-square. So there are 5 or 6 other statistics that are available still, but there is one paper from Skinner from 2009 where he compares the empirical utility of all these models, including these two statistics, and he finds that actually these two adjustments are the most unbiased. You wanted to say something? Because you raised your hand.
No.
Okay. So this is RALSA, the chi-square adjusted statistics is proven to be the most unbiased estimator for cluster data, which is in our case in TIMS it's cluster data because we select entire clusters. So we see that in Italy the relationship between these two variables is not statistically significant, the p-values when you look at the end. So gender and how much students like learning science are unrelated. But it's also the same in Spain, it's also the same in France. Now if you go to the next sheet, what you're going to see here is so-called heat map or heat plot. And what I have see done here is one of the things that are helpful is not only to put the number of cases, but also to highlight by the number of cases. So we see that in both sexes, it goes pretty much uniformly. You know, all of them. If here it would be a bit different the other way around, and for male students it's here. Then you could say, you know, that they're going into opposite direction, and then most probably the relationship between the two would be different. And it's quite similar in France. So actually the distribution between these two is quite the same. Because we don't have any splitting variables to do these plots by some other categorical variables in every single country, at the end we have this big plot of combining the plots of Italy, France, and Spain together in one single plot. And then we have again the analysis information and so on. Yes, Herman, please ask a question.
Question between, yes, I understood that the two significance tests that we do need them for the two columns, but may I be right, we use them for the two rows, right?
I'm not sure that I understand.
So we get these two significance tests.
Yeah.
And I understood that we would use them for the two columns, but we are using them for the two rows, for the male and female row, or not?
No, it's relationship between the two variables. Now, this thing with the cross tabulation is just distribution of the values across the table, the observed and the expect. But the high square is testing the relationship between the two variables. It's not strictly a tabular thing. So not quite sure maybe if I understand your question correctly.
I will follow this.
Okay.
Thank you. But in the end, we see that the difference is not significant, right?
Yeah, it is not significant. This is what they say.
But the difference between, it says the difference between male and female is not significant, but perhaps the difference between countries, if we would, no, but that doesn't make sense.
But
No. Sorry.
Not sure what you
Sorry.
Okay.
Sir, can you repeat what is first order and second order?
Aha, okay. Just a moment, I closed it, but I'm just gonna run it again. Lazy to look at it for it on the system. Well, that's a good question actually. The thing is, the difference between these two, the first and the second order, is how the high square and is computed using different degrees of freedom. I'll show you now when it opens the table. Okay. So it is using here the degrees of freedom by the number of categories in the row, if I remember correctly. I don't remember the formulas by heart. I'll just delete these because I don't want to mess up the screen. So here you have, in the second order, you use the degrees of freedom. So this is, you have three categories in column variable. Not at all, very much, and kind of. So it's 2 minus 1. But here in the second one, the second order, you are using the sample degrees of freedom and the design degrees of freedom. What is the design degrees of freedom is the number of replicates, because we have cluster data. Again, I have to check and read what exactly it was because I don't remember all the formulas by heart. But yeah, that's the difference between them. And the other thing is, there are statisticians that actually say that, well, the first order of these statistics was invented, of course, first, and then the second, you know, in another attempt to account for the design itself, of the cluster design in a better way. But then there are quite a lot of statisticians that say that nevertheless the first order is less biased than the second, although the second was intended to be as an improvement.
So this means in order to report it as significant, both should be significant. Or can you argue that it's enough to have the first one significant, first order significant?
These are two different tests. It is like you make a regression and then you say, yeah, by the p-value of the regression is not significant, but when I do the confidence interval, it is. You know, usually I haven't seen so far if one is significant, the other isn't. Normally they both would appear, or both will not appear. Of course, there can be differences, you know, between them. But it's, yeah, how to answer this question? Normally you would report both and then comment. If one of them appears significant and the other one, I would just put a hesitation in the paper when I report this and say, well, I'm not sure, I'm not gonna, you know, make a definite decision this is significant or not significant.
Obviously, in the scientific paper, you can do so much when reporting to the public or to.
I would just say
It's
that,
up to Olga,
it's inconclusive.
Yeah, that's
It's inconclusive.
yeah. That's the same as not significant. So it means we have no significant result.
Yeah. Okay, next one is correlations. And let's go and choose the data file again. Now, I realize that it may be quite boring choosing the same data file over and over again for every single tab, but unfortunately, R is operating only in the random access memory. So once you close the application, then everything is gone. And next time it starts from scratch. But the other thing is that when you use different data sets for different kind of analysis, this actually can be convenient because in every single tab you can load different one. So we have two correlation coefficients that we can use, Pearson and Spearman correlation. You know what is the difference between them, right? Okay. So now we're going to compute that's actually a bit of a pedagogical example. Students' bullying and overall science scores. We'll scroll down. I'm not going to split by anything, I'm just interested in the correlation on country level.
It's not possible to choose both Pearson and Spearman in the same time?
Well, it's either one or the other.
Only SPS.
In SPSS.
Yeah. It's not possible.
No. So I'm gonna add student bullying as a background variable. Now, be careful, there are two of them. One of them is the scale, which is the continuous, and one of them is classified into categories. So take the scale and move it as a background variable, and then go and find in the plausible values, first to fifth plausible values in science. Okay, select it, and then move it against plausible values. Okay.
I thought the SCL was the scale and indices, and the
Scale.
index was the
SCL is the continuous. Okay. Now scroll down, leave the total weight, total student weight, overall weight as it is, and define the output in work outputs correlations or something like that. Okay. Click on execute syntax. This one is a bit more computationally intensive. Okay. It is done. Now, you have a number of cases, again, estimation. I didn't put any splitting variables, and because it's computing on country level, this is why it's going to be 100%, because we don't have any categories to split by. Now, you have here like a correlation matrix. The variable plausible values with itself is going to be, of course, correlation of 1. And then the other one is the background variable, Boolean, and also the plausible values in science. You see the correlation coefficient. And you also see here further, you see the standard error. Now, if you scroll to the end, you will also see the p-value for that one. Now, it's because 0.000, it means that we have, you know, it's so small that it appears as a scientific notation. So I normally like to be, because I know that we have noise in the data, like in these cases still to report p-values of 0.05, just to be on the safe side. I know that we have noise there, and cannot be so precise, you know, in the estimation. But still, it shows me that the correlation is statistically significant. Now, if you check in France, in Italy, and then also in Spain, we have positive correlation, and in all 3 countries is statistically significant. So now remember that the variables was the student being bullied at school. So what is the conclusion? Beat them up and they're going to achieve higher, right? Now, the thing is that everyone is so silent, scared to say anything. Okay, One thing that is not documented in the technical report of TIMSS, and nobody tells you, actually, it's not also in the user guide or any other document from Boston College, is that they actually reversed it, so higher values mean being less bullied. And you don't find it. Just by chance I talked to somebody from Boston College a few years ago, and then he told me that, yeah, I know that it's confusing, it's actually the other way around, but then the scale is not named properly, and then it's very confusing. So it's always the other way around, actually. So, yeah. So the correlation actually is negative, it's not positive as it's shown in the Excel sheet. Okay, Herman, do you have any questions?
They should correct the user guide. It's
Yeah,
the
I know.
online version.
I know, and there was last week, there was, no, the week before last week, there was a NRC meeting with Boston College, and I suggested that, and they just said, yeah, maybe we should fix that. But this is actually happening since 2015, it's not. Anyway. I mean, they can keep it as it is, I don't mind. It's just that at least there should be some documentation on that. But it's just confusing. Okay. Okay, other questions? No? Okay, let's do then the next exercise. Linear regression. Okay, now switch to that tab, linear regression, and choose the data file. Work, merge files, student. Okay, and now we're going to compute linear regression coefficients. The overall mathematics achievement is going to be our dependent variable. You're all familiar with linear regression. You know what it means, right? Okay. Now, let's take the mathematics. We're going to search for the plausible values, first to fifth. And then scroll down and okay, when you see the dependent background variable. So just above that, you're gonna have choice. Sometimes you may want to have a background variable that is dependent. Depends on your interest. Sometimes it's gonna be achievement scores. I'll click on plausible values. I should have actually checked this one first, and then look for the plausible values in mathematics and select it and put it there, because it just resets all the selections. Okay? I'll scroll down, make sure that here the dependent variable is plausible values. Then add it. And then I'm gonna use two scales: how much students are confident in mathematics and how much home resources students have at home. So these are the two variables I'm going to regress the plausible values on. Okay, now I'm going to, what did I say, confident, students confident in mathematics. Okay, select the one that ends with SCL, not the IDX. Okay, and then make sure that you move it under independent background continuous variables. Okay, and then the other one is home resources for learning. So these two are scales that are composed by many background variables. Okay, make sure that you take again the SCL1. So you should have at the end these two as selected. Are you all there? Yeah. Now, scroll down.
Well, there could be interactions.
Yes, there could be interactions between these two. Okay, let's check the interactions between these two. Okay, yeah. Okay, define the output file name. Work outputs. I will just name it linear regression. Okay. Save. Okay. And then at the end, click execute syntax. Now, this is going to take a bit longer because it's more computations to be done, but it's still going to be not going to be so complicated.
What is the implication of use shortcut method for computing standard errors?
Yeah, that's for compatibility with the reports from previous cycles. Because until 2015, before 2015, Teams and Pros had actually the replication weights. They have been done replication within each zone just once. So in each zone they kick only one of the schools and compute with the other. And then in 2015 and later, they decided that they're going to do it twice per zone. So once with one of the schools, then recover, and then compute it, the thing that I presented with the table with the replicate weights. So it's done 150 times instead of 75 times. And on top of that, for computing the standard errors, the final standard error, the imputation variance included only the first plausible value. That was a shortcut that was applied for a very long time, just because in 1995, when the first TIMS appeared, the computers were not so powerful. So it was taking them 2 days just to compute a mean. And then, in 2015, they decided, well, computers are powerful enough, let's just get rid of the shortcut already. So that's why it's called a shortcut. The thing is that if you try to replicate the estimates from the older reports on Teams and Pros prior to 2015, then you will have a problem because you're going to get a different number. So this is for compatibility with the previous versions of all the softwares. Okay. Now, what we're going to have is, we're going to have, besides all the population and sample statistics, we're going to have the intercept, which would tell us how much is the average achievement in the country when controlling for, taking out the effect of the two independent variables. And then we're going to have the coefficients of the for the independent variables with the standard errors, and then we have the components of the standard errors and so on until the end. And then we're going to have also the p-values. So we see that even after controlling for the first one, which is how much students like mathematics, the home resources for learning in Italy is still statistically significant. The p-value is less than 0.05. Okay? And then we have also, as requested by Herman, here the interaction that is divided by column. The interaction between the two independent variables. Well, sorry, have the interaction is not statistically significant. But it could be, no? With other variables. It is also not statistically significant. Well, look, it is in France. Is it France the first one? I forgot. Yeah, in France, it is statistically significant, and in Spain, it is not at all. But in Spain, both predictors are statistically significant, and also in France. Well, why? I cannot tell because I'm not so familiar with the context of education in all three countries. But it could be also some social variables that are not part of the educational system itself. Now, in the second sheet, we have the model statistics. We have the R squared and the adjusted R squared. So we see that actually in Spain and in France, the explained variance is much larger than in Italy. And you also see that the explained variance and adjusted explained variance are not different at all. I mean, at least on the second decimal in all three countries. Yeah, they have some difference, but it's minuscule. You know what is adjusted R square, right? Adjusted R squared is the explained variance when you adjust for the number of predictors, because more predictors you add to the regression model, of course more explained variance you're going to have, and this is adjusted for that. Okay, and then the analysis information. Now, remember the case that we had with computing the average achievement of boys and girls. So we saw some confidence intervals where we couldn't actually say whether the difference is significant or not. And this is the next example that we're going to have with RALSA. We're going to compute the significance of this difference. So I'm going to take all of the variables out, the independent variables. I'm going to use the mathematics here though, because we're still going to use that. Okay, let's do it science for the variety. Okay, so leave here the dependent variable. Wait a moment, I'm just going to. The dependent variable will be plausible values, but we're going to go and select the science. Okay, I'm going to select it and then put it as dependent plausible values. Okay, and then
It's a little bit too fast. So,
Yeah.
okay, I'm sorry. Yeah.
so we keep the independent and we just have changed the
No,
dependent.
also remove the independent.
Oh, okay.
Also,
Sorry.
okay.
Yeah.
It was simply. Perhaps we have been sleeping, sorry. So, but it's
Sorry, what was that?
Perhaps we have been sleeping. Is there a new independent or is there no independent at all?
You won't be able to run any model if you don't put independent. Okay, so now you all added science course as dependent. Okay. Scroll up and then look for sex in the list. Select IT sex. And now we're gonna put IT sex as independent background categorical variable. Okay. So now you see IT sex, sex of students, So afterwards, it recognizes how many distinct categories it has besides the missing values. So it is 2 categories, boys and girls. Now, when you look at the next column here, it is called contrast. So it has dummy, deviation, and simple. So if you want to know what is the difference between them, you can switch to RStudio and search in the help of RStudio. LSA linrec, this is the function. And then you're gonna have in the details section a description of the 3 different contrast scoring schemes.
Where do you have the information from that you put in there now, the LSR lean rec? Or because it's that's a specific help file for RALSA?
Every single package that you install, it comes with help for every single function. So when you go to RStudio and you look for every single function that is available, you first have to load the package, and then it gives you can search for help for every single function. And that's a must. You need to have a reference manual when you produce the package. So you see, the first one is dummy. So I'm not going to go into many details. There are different contrast scoring schemes depending on what exactly question you want to answer. So the intercept is going to be the average for the reference category. The reference category is the one that you choose that you want to compare with all other categories. And then the coefficient that you will have for the other categories is going to be the difference with this one, the average difference. Now, when you have the deviation is the grand mean, so it's not the average of this, but it's the grand mean of the dependent variable regardless of the groups. So if I choose this one, then I will have the mean of boys and girls together, and I'm gonna compare the one of them to this grand. So I'm gonna pull everyone together. And then simple is the same for dummy, so it's going to be the average for the reference category, boy or girl, depending on what I choose. Except for the intercept, which in this case is going to be the grand mean. So you see that they're similar, but not exactly the same. So in this case, I'm just going to leave dummy coding because I want to compare boys and girls. And then it asks you which one you want to be the reference category. So if I choose female, it's going to be the average, the intercept is going to be the average for girls, and then my coefficient is going to be the difference in the average score for boys with the girls. Okay, I'm gonna use I'm gonna leave it as female and dummy. And then I'm going to scroll back to the end. I'm not going to change the output file name, just make sure that you close, if you also not going to change it, just make sure that you close the Excel file in advance. Then at the end, click on execute syntax, and now we're going to wait a bit.
No, no,
Okay. So now let's have a look on the output. We're gonna have also the descriptive statistics for the sample and the population. We're not interested in that. So now in Italy, the intercept is telling us that girls, who are our reference categories, have on average 596 points. 500.96. Okay, this is their average achievement. Then boys are our comparison category, and they have 7.5 score points higher. So now remember, this is a categorical variable where we compute, regression with it, and it gives us the estimate for the different categories. If we go to the end of this output, we're gonna see that the difference is statistically significant. The last column shows us the p-value. Okay? And it is not, however, in France. Is it France the first one? Yeah, France. It is not statistically significant in France, where boys actually achieve 1.83 score points lower. And in Spain, it is also not statistically significant. So now, remember from the classical texts on statistics, yes, there is a statistically significant difference. Is it practically significant? Is it important? So yes, it is statistically significant in Italy, but it's 7.6 score points on a scale of 500 as a center point and standard deviation of 100. So that's not even 1/10 of the standard deviation. So yes, it is statistically significant, but should you do something about it if it's so small? I don't know. Depends on your agenda. The other thing is that you can, this result, okay, I closed it. This result also is analogous to t-test. I don't have t-test in RALSA just because I take the linear regression as a t-test when I have variables with just two categories. But if you don't believe me, you can take any data set and just in SPSS or any software on your own, you can test it with linear regression with dummy coding or t-test, and then you compare the results and you're going to see that it's exactly the same. So this is actually a shortcut for t-test. Now, one of the things that people are missing here is having the classical ANOVA analysis of variance, and some people really want to have it. There are some computational issues with that. Remember when I was talking about the cross relations and the Rouse-Scott adjustments? With cluster data, we have the problem into cross relations, but with ANOVA, with cluster data, we have very similar issue that the F statistics is going to be biased. There are ways to overcome that with other series of adjustments for ANOVA. But it's hard to implement. It's on my list to add ANOVA, classical ANOVA to RALSA. But the other thing is that you can use, instead of ANOVA, you can use linear regression with contrast coding when you have more than two different. No, I'm not going to take let's take any of the indexes that has 3 categories. Let's say student with school belonging. No need to follow me. It has 3 categories, high, some, and middle. I'm just gonna use everything as default and just execute it. So the output is going to be very similar. The difference, however, is going to be that when you have more than 3 categories, you're gonna have coefficients for the second and the third. When you have more than 2, sorry. In this case, I have 3. If I can have 5 categories, then it's gonna have 4 coefficients for the last 4 that are not my reference category. But the logic of comparison is just the same. Now, when it's gonna compute, I'm gonna show you. So your intercept is going to be again the average for the people that belong to the reference category, and all the rest is going to be the difference with that mean. So it's not like ANOVA, but it's a substitute that you can use with it. For it. Okay. Okay, so now the logic here is the same. So it was high, medium, and low. So our high category is our reference category. So the students that choose this one, that actually fall into this category, they have 494 score points on average. Then the ones that are medium are 6.7 score points lower on science achievement. Science achievement. And then the ones that are low on that one, they're 30 score points lower than the ones that are high. And you would see that while for the first one, for the medium and high, the difference is not statistically significant, but it is for the high and low. And in France, at least, it's quite sizable, but also in Italy and also in Spain. The good thing about these things is, whether you use it as a substitute of ANOVA or for t-test, is that you can also add variables that you want to control for. When you want to see, when I control for this, how the relationship between these two change. Yeah, the difference is decreasing. So you can, if you find something important about a certain construct that is important for you and it's relevant to Italy, then you can, go further and maybe advise something to the policymakers. Questions? Okay. Now the last one is going to be a confusing exam, but that's on purpose. I know, I'm mean. Is to compute binary logistic regression coefficients. So binary logistic regression is applied when we have the economous variable as a dependent variable. Yes or no? So we have only 2 categories as a dependent variable. So let's choose the student data file. Oh, where am I going? Looking outputs in merge data. Student. Okay, now we're gonna compute binary logistic regression coefficients predicting the loyalty odds of students agreeing a lot they like being at school as a function of students being bullied and students' sense of school belonging. Now remember our example from the very beginning when when we were recording variables. So we're gonna use the new recorded variable that is actually exactly this one. How much students agree they like being at school, and we're gonna add the two predictors of school belonging and student bullying. Okay, so scroll down and you see here dependent binary variable. So I'm going as a variable name, just gonna put REC because this is how I name the variable at the end. Recoded. Students like being at school. I'll scroll down. Dependent binary variable, I'm gonna add it there. Okay. And then I'm gonna add the two scales. I'm just gonna search them by variable name. ASB, GSSB. I'm gonna zoom it now so you can see it there. This is the okay, sorry. Excuse me for a moment. I would like to add them in the order that I have put them here. Okay. Student bullying, it's one less S. ASB, GSB.
It's independent continuous backward.
Yes, independent continuous background variable. Add it there. And then the other one is going to be ASB, GSSB. They're very similar names. I'm also getting confused between these two. That's a student sense of school belonging.
It's also continuous, right?
Yeah, it's also continuous. Now, add it there. I need to select it first.
Sorry, ASB?
G?
SS.
Yeah, the second one is SSB. Okay? Okay, scroll down to the bottom. Now, you will see one checkbox here, the first one, that says normalize weights. Click it. I'm not going to explain you now why. I'm going to say a bit later.
And standardized coefficients sounds also good.
If you wish. I'm going to leave it blank.
Because I do not know how many, whether it's a 4-step Likert scales or, oh no, these then it's not.
They're continuous variables. And they're on the same metric.
Yes.
Okay. So click on normalize weights and then define the output file name. RALSA workshop, work, outputs. Just gonna name it binary. Okay. Save. We see the syntax and then execute. And it's gonna take more than 1 minute. I just need to go to the bathroom very quick now. I'm just just gonna switch to the presentation because there I have all the comments written in advance, taking Italy as an example. Okay. Now, so these are the results for our binary logistic regression. We have significant coefficients. Look at the P column, p-value column, which is, does it show what? Okay, it doesn't show my mouse cursor. So we have significant coefficients for student bullying and school belonging. So the coefficients for bullying are negative. Now mind that the scale is reversed. Again, it's a very confusing example, which the purpose here is not to scramble your brains, is just to point that you need to read the documentation and hope that everything is documented. But no, I'm not making fun of it because it's very often, even now, I sometimes think, I mean, I have long experience with these databases, and I think that actually I have, you know, all the knowledge, and sometimes I just miss important details. So lower values of bullying means students are more often bullied and vice versa. So that's the odds of the event liking being at school at the same time decrease when a unit increase in being bullied after controlling for students' sense of school belonging. Now the things became really complicated. And at the same time, the coefficients for sense of school belonging is positive. So the odds of an event happening are increasing with unit change in school belonging after controlling for student bullying. Now, so binary logistic regression is complex enough by itself. And when you have, you know, such a crazy mess of variables, now things become even more erratic. So with the odds ratio, this is the changes in odds when our independent variable is increasing or decreasing with 1 unit. So for student bullying, you know, the crazy variable, the odds ratio is lower than 1. So what this is showing us is a negative relationship between student bullying and students like being bullied at school. But as the frequency of bullying decreases, the probability of liking being at school actually increases, which is expected because of the directionality of the bullying scale. For sense of school belonging, the odds ratio is greater than 1, so positive relationship between sense of belonging and liking being at school. So being less bullied and having stronger sense of belonging has a positive effect on student liking being at school. Effect I should put here in quotes because people normally are getting really mad when they hear that in social sciences. So, but the other thing is that for each unit of increasing in student being bullied, direction again, the odds of liking being at school decreases by a factor of 0.89, which is this guy here that doesn't want to show my mouse cursor, but you see it on the screen. So a unit increase in student being bullied, the odds of liking the school decrease by 11%. We just take the difference and multiply it by 100. For each unit increase of student sense of belonging, the odds liking being at school increase by a factor of 0.465. And at the end, a unit increase in student sense of belonging at school, the odds of liking being at school increase spectacularly by 365%. You just take the, what?
So there must be a very high.
Isn't it the opposite for the first
Yeah.
point? Because an increase on the bullying scale means less bullying, correct?
Yeah,
So
you see
one,
even
so
on-
one unit increase in less bullying is predicting less liking of
Yeah.
school. So isn't it the inverse of this?
Yeah, you see, even I'm getting confused with this example. So yeah, it is.
Decrease
Just
instead of increase.
Sorry?
So it's decrease instead of increase.
Yeah, in the last sentence.
Decreases.
And the
Yes.
increase in bullying.
You mean the
No,
distance?
I'm talking about the
No,
first
no.
two bullets. The first two bullets.
Okay, that's right. Sorry, I'm also getting tired of, yeah. Which meaning the increase in student being bullied. The odds of liking being at school decreases by 0.89. Yeah,
So it should be that each unit decrease in student being, or flip one side of the sentence. Right?
We have to think through this again.
yeah, because, yeah, you see, I mean, I'm so sadistic that at the end I tortured myself too. Yeah, but again, because it's this one, this is the bullying one.
Yeah.
So it is 0.89, but it is, yes, decrease, mind the directionality, and then I forgot to mind it. Okay. You are gonna bold it. Okay.
The second part was right. Right. I mean, it's.
No, wait. Yeah, okay. It's crazy. Okay. Okay. Then for the odds ratios, we can say that the odds ratios of being like in school has been over 0.89 times lower direction scale. Okay, this one is correct. Then a student who has been less bullied with 95% confidence interval between this and that value. So the lower and upper confidence interval bounds for the student being bullied are below 1. So as more the student is being bullied, the odds of liking of being at school decrease. So sorry, yeah. I should for the next workshop I should change the example. This is just insane what I did here. But again, it shows it.
You wanted to achieve a lot. You wanted to explain to us the complexity, and also you wanted to hint us to this.
To the analysis itself, yeah.
Yes, and to take care of the of questions of coding.
Yeah,
this
you see the consequences. Yeah. I was too ambitious with this example. Okay. Okay, so we also have these. We also have the model statistics. So, just gonna walk quickly. We have the. This is supposed to be animated. Okay. So the first one is the null deviance, how well the response, the response is predicted, the dependent, binary dependent variable by the model with no predictors. So this is just the intercept of the model, so that's the model fit. And then we have also the second one, the deviance itself, when we add the predictors. So how well actually the response is predicted. Then we have the degrees of freedom for the null model without any predictors, then with the full model with predictors. And then we have some information criteria, the high square and and then we have different different R-square statistics for the explained variance. All of them are adjustments of each other at the end, and with model with so many with just two. They're quite similar, except for the last one, which is the adjustment of Cox and Snell. If I remember, the last one is actually the most, the newest one. Which one is best to report? I would report all of them in the paper. I wouldn't limit myself and say, choose just by convenience the last one because it's the highest. I said also at the beginning of this example is that I'm gonna do normalization of the weights, and I'm gonna explain later. And while I'm explaining about it, I'm actually going to go back to RALSA and turn it off. I'm gonna close the output and then execute the syntax, because it's going to take some time. So while I'm talking, it's just going to compute. So with binary logistic regression, we have the problem that if any one population that is the sample comes from, it can be oversampled. But then it happens, actually Italy has it, oversampling of certain population. If I remember correctly, you had it by private-public schooling, and I forgot which one was the other one. Computed quite quick this time. Okay. So the other thing is similar problem is in South Africa, where they oversample the private schools, and on top of that they oversample because of measurement problems. The problem is that they have quite a lot of heterogeneity in the population. So Slovenia, where I live, for example, it's a small population where absolutely everything across schools is the same. Even the hair color of the school principals is the same. They're just trying to achieve complete uniformity in terms of, especially of resources given to schools. So if one school is given tablets for students, then all schools should be given tablets for schools, no exceptions. And that's by the budget policies in the school. But in South Africa, the things are very, very different. There you have private schools that look like castles, and they literally have golden handles on the doors. And on the other extreme, you have schools that are just designated area in the field. They're very poor schools. They don't even have a blackboard. And that's why the TIMSS 2015, no, TIMSS 2011 sample for South Africa was 12,000 students instead of the required 4,500. But when you oversample the population for this purpose, and also you do it because you want to represent sufficiently certain parts of the population, then you end up with different kind of ways than you would do normally. because you need to assign, for underrepresented parts of the population, you need to assign equal weights. So, and the consequences of all this is that normalizing the weights is that the number of elements in the population, so we need to normalize the weight to adjust for all this. Otherwise, I will show you in a moment what happens. We get gibberish in the output, so the population will sum the number of cases in the sample. That's the consequence of this. But actually, it will treat the sample as a population and at least will give you an estimation for the coefficients. So these are the coefficients for France from this logistic regression model that make absolutely no sense. It doesn't always happen. It happens to some in some analysis. It doesn't happen in other. The problem is that when we have extreme weights, we need to normalize them because otherwise we're running into the problem of perfect separation between the 0 and 1 category of the dependent variable, and we end up with this kind of gibberish. And it doesn't hurt at the end to apply it. Okay, sorry, actually I was wrong. Sorry, this is my mistake. At the end, it actually does sum to the population when we apply the normalization of the weights. Now, some of the things, we still have 15 minutes before we finish. Some of the things that I think you may find useful in RALSA. You have a help section. These are links to the RALSA support website that you can link that you can use if you need help. The other things that I think that could be useful for you is you can produce variable dictionaries. So this is similar to the variable dictionary command in SPSS, where it lists the variable, the labels, and then the value labels. The other thing that and you can choose which ones. The other thing that I think you will find useful is that before doing the actual analysis, you can make diagnostics of the variables that you're interested in. So let's say I want these two categorical variables. Sorry, I'm not going to take these two. I'm going to take these two, and I'm going to split them by 6. And on top of that, I'm going to take some of the scales. Which is a good diagnostic statistic. Just have in mind that these are not statistics that you can use for reporting in your paper or your national report. This is just for diagnosing the properties of the variables that you're interested in. So you're gonna have here, it will tell you in case you forgot what you did, which is the study, the respondent, the cycle, and which weight it is used. So this is weighted diagnostic statistics. And the good thing is that you can also click and navigate, and it's going to show you by country, by gender, how much do you have even different kinds of missing, user-defined missing. And when it comes to continuous variables, it will show you by gender what is the minimum, the maximum, the average, and the variance. just simple weighted statistics. You found something? No, I mean, because I thought that you have a question, or?
No.
Okay. And then you can even go back to the title sheet. One of the things people are asking me, what are the advantages compared to other softwares, is that first you have a graphical user interface, which is not true for other R packages. The IDV Analyzer has a graphical user interface, and this year they finally added our option. It doesn't, however, cover all the functionalities that RALSA has. For example, you don't have the cross tabulations, you have limitations in the linear regression, and also you don't have the all the graphical representation that RALSA is offering. They don't have their own recording of the data. Like, no, you still have to go back and do it by yourself in SPSS somehow, and then come back. You don't have the diagnostics, and so.
And they also don't have, but you also don't have the some tool to correct for the cluster effects. So for type complex, what is type complex in M+, for instance, you cannot correct for the higher probability to get significant results due to the sampling of students in schools.
Yeah, but give me example of analysis that is done.
Yeah. When you want to do, for instance, when you, as I learned, you may overestimate significance if you use clustered data in linear regression without correcting for the data being clustered. Therefore, in M+, you use type complex, for instance.
But this is exactly what you're doing. Yeah, but in which analysis? In the regression?
Yes.
This is exactly what you're doing with the replicate weights.
What do you do?
Yeah, that's why they were invented, to correct for the clustering effect.
Thank you.
So, I mean, I hope that you enjoyed this. And actually, in Slovenia, we had series of workshops of school coordinators of schools that were participating in ICCS and also in PEARLS. This was last summer and the beginning of autumn, where we basically went around the entire country giving these workshops for students and for teachers, I'm sorry. It was part of our return for them as gratitude for participating in this. So, and these were teachers in Slovenian language, because these are the ones that do the reading instruction, and also in grade 8 civics education. So it went surprisingly well, even to me actually, because one of my goals was actually to bring this tool to make the data more accessible to non-technical users. And there is now a project that we're applying to the ministry that next year they sponsor a series of workshops for more teachers to be done there. So do you have any questions? Because we are closing already the session. I believe we're until 6:30, so our friend there is gonna kick us out if we go beyond. I'm joking. Yep.
Part of this is I think I just need to think through it and look at the technical documentation, but if we're doing a study in a country, we want to compare like our sample to sort of population sample, right? So like how similar is our sample of schools to what you would expect based on the test, for example, right? How would you go about doing something like that? Like, is there a way to kind of export, I guess, like, could you point R towards our data that's generated from this that's weighted, and then compare it to a given school? I know earlier you said don't compare it to school, but if you have a separate sample, you're trying to see how similar it is to the population.
Well, it's not part of the same sampling frame, I think. So, if I understand correctly, we draw here a representative sample in TIMSS or any other large-scale assessment study, and you want to compare the population estimates against another sample. Okay, let me open one of the outputs. Am I blind? Ah, no. Data or outputs. In a way, actually, what we're doing with every analysis, and this is also what the IDB analyzer, for example, is doing. At the end, it computes the table average. So it is average of all countries. I mean, there are special formulas that actually are used to summarize the statistics. If you look at the technical report of TIMSS or any other study, there is also usually a description how the tables are computed and the countries can be compared when you compare one country to the other. So going back to your question, if you can ensure that the sample that you are comparing to this sample, and you are able to compare it in every other respect, like target grade, target age, and so on, then you can treat them as two separate countries and use the same formulas that are in technical documentations of this. Because the logic is the same. But you need to make sure that the other sample also is also subject to the same technical standards that are used in TIMSS and PROS. Otherwise, you're going to be comparing apples with bottles. With bottles. Apples with bottles. Because they end with S, you know.
Yeah.
Other questions?